Good morning, all of you. My name is Sai Kiran. I'm your chemistry lecturer. In our last class, we discussed important basic terminologies related to atom. They are atomic number, mass number, average atomic mass, isotopes, isobars, isoelectronic species, and few more. Today, we will discuss development towards Bohr's model. In between Rutherford model and Bohr's model, two major developments is there. They are dual nature of electromagnetic radiation, and second one is atomic spectra. Now come to the first one, dual nature of electromagnetic radiation. Electromagnetic radiation can behave as wave nature as well as particle nature. Now we will start with wave nature of electromagnetic radiation. According to James Maxwell, when a charged particle moves under acceleration, electric field and magnetic fields are produced and transmitted. For example, this is a charged particle, whether electron or proton, moves under acceleration. It produces electric field and magnetic field. These fields are transmitted in the form of waves. These waves are called as electromagnetic waves or electromagnetic radiation. Now come to the properties of wave nature of electromagnetic radiation. The oscillating electric field and magnetic fields and the oscillating charged particle perpendicular to each other, and the electric field and magnetic fields perpendicular to the direction of the propagation of wave. Let's understand. This is the direction of propagation of wave. This is electric field. And this is magnetic field. These three are perpendicular to each other. Let's understand. This is the direction of propagation of wave. This is. And this is the electric field. This one. And this is the magnetic field. The angle between these three is 90 degrees. These three are perpendicular to each other. Now come to the next property. We know that sound waves and water waves, they need medium. Without medium, they can't travel. But in case of electromagnetic waves, they do not require any medium. They can travel in vacuum, like sun rays. Now, this wave nature is proved by two phenomena. One is diffraction, and second one is interference. These two phenomena you can study in your class 12 physics. Now, I will give you a small introduction about these two phenomena. The diffraction is nothing but the bending nature of light. When a light, this is the source of light, passing through a prism, it forms waves. This is due to bending nature of light. This is called diffraction. And now come to the interference. Interference is nothing but when two waves are fallen at a time, the resultant wave is called interference. It is divided into two types. One is constructive interference, and second one is destructive interference. Let's see, what is constructive interference? This is one wave, and this is another wave. This is crest of one wave. This is the crest of another wave. The resultant wave is the sum of these two waves. These two waves are called in phase. The resultant wave is bigger than these two waves. This wave is called constructive interference. Now come to the destructive interference. This is one wave, and this is another wave. This is the crest of one wave. This is the trough of another wave. Because of this trough, the height of this crest is decreases. The resultant wave is like this. The decrease of this wave is called destructive interference. These two phase waves are called out of phase. Now come to the characteristic properties of waves. The first one is wavelength. It is indicated with lambda. For example, this is a wave. This is called crest and this is called trough. The distance between two successive crests called wavelength, or the distance between two successive troughs called wavelength. In other words, the distance between one complete wave, the distance of one complete wave is called wavelength. Units are meters, centimeters, angstroms, picometers, nanometers. Let's see the conversions. 1 angstrom is equals to 10 to the power of minus 8 centimeters. That equals to 10 to the power of minus 10 meters. 1 nanometer is equals to 10 to the power of minus 7 centimeters. That equals to 10 to the power of minus 9 meters. That equals to 10 angstroms. 1 picometer is equals to 10 to the power of minus 10 centimeters. That equals to 10 to the power of minus 12 meters. These conversions are useful for problem solving. Now come to the second one, wave number. It is indicated with nu bar. It is nothing but the number of wavelengths per unit area. For example, this is a 1 centimeter, 1 unit area. In this is 1 wavelength. How many number of wavelengths passed in this unit area is called wave number. For example, this is 1. This is another one, 2. This is another one, 3. This is another one, 4. 4 wavelengths in 1 centimeter is called wave number. The number of wavelengths in unit area is called wave number. In other words, wave number is nothing but reciprocal of wavelength. Nu bar is equals to 1 by lambda. Units are centimeter inverse, meter inverse. Now come to the next one, frequency. It is indicated with nu. It is nothing but the number of waves passing through a particular point in 1 second is called frequency. For example, this is a point. The number of waves passing through this particular point in 1 second time is called frequency. Units are hertz or second inverse. The relation between frequency and wavelength is nu is equals to c by lambda. Here c is the speed of light, that is equals to 3 into 10 to the power of 8 meter per second, or 3 into 10 to the power of 10 centimeter per second. Now come to the velocity. It is indicated with c. The general formula of velocity is equals to distance by time. Similarly, the distance traveled by wave in 1 second is called velocity. Units are meter per second or centimeter per second. The all type of electromagnetic radiations have the same velocity, which is equals to the velocity of light, that is equals to 3 into 10 to the power of 8 meter per second, or 3 into 10 to the power of 10 centimeter per second. Now come to the time. It is indicated with t. Time taken by a wave to pass through one point is called time. Time is inversely proportional to the frequency. Now come to the amplitude. Amplitude is nothing but the height of the crust or depth of the trough. This is the height of the crust, amplitude. It is indicated with A. The depth of the trough is called amplitude. Amplitude is a measure of intensity of beam of light. Intensity is nothing but brightness of the light, and it is independent property. It does not depend on any other property of wave. Units are centimeter, meter, picometer. Now come to the electromagnetic spectra. This is the region of high wavelength and low frequency. This is the region of low wavelength, high frequency. Based on these different wavelengths and frequencies, electromagnetic radiations are divided into many types. the different types of electromagnetic radiations arranged in such a way that increasing the wavelength and decreasing the frequency. The arrangement of these radiations is called electromagnetic spectra. Let's see. First, gamma rays, less wavelength, high frequency. And next, X-rays. Wavelength is 10 to the power of minus 10. Frequency is more. Next, UV rays. Next, this is the small region. This is visible region. We know that visible region contains 5GR, violet, indigo, blue, green, yellow, orange, red. The wavelength is 400 nanometers to 750 nanometers. In electromagnetic spectra, we can see this region only with our eyes. Remaining all rays we cannot see because the size of these rays is very small. We know that atom size is very small. We can't see with our eyes. These ray size is smaller than atom. Now next is IR rays. Next, IR rays means infrared rays. Next, microwaves. And last, radio waves. Radio waves has the highest wavelength and least frequency. This is the electromagnetic spectra. You no need to remember these all values. You just remember the order. Then you can answer the questions. That's it today class. In our next class, we will discuss particle nature of the electromagnetic radiation.